Yeah, thanks a lot for the invitation and the chance to present a monitoring program using Pléiades satellite images. I'm a CNRS researcher. I work in Toulouse, southwest of France, in Lagos, which is one of the laboratory of Observatoire Midi-Pyrénées. And I want to illustrate how we provide to the community a resolution digital elevation model and ortho images from very high resolution images from Pléiades. The context was already nicely introduced by Andrea in his talk, is that glaciers are really under pressure of global warming. This is a complex figure from a paper published back in 2021 that show a comprehensive view of glacier mass loss on Earth. So the size of each square is proportional to the mass loss of each region on Earth. So you can see that Svalbard in the far north are indeed losing mass, but everywhere on Earth, glaciers are losing ice. So that at a global scale, for this period of 20 years, from 2000 to 2020, they lost 260 gigaton per year. It probably doesn't tell you a lot, but this is equivalent to 3 Olympic swimming pools lost every second. And this is lost to the ocean. So glaciers are contributing to sea level rise about 3/4 of a millimeter per year. This is about 20% of sea level rise. Important to remind here, we look at glacier, what some people call sometimes mountain glacier, but this excludes the two polar ice sheets of Greenland and Antarctica, which are also contributing a large fraction of sea level rise. But here, the presentation and more observatory focus on glacier. This mass loss of glacier is also accelerating. For example, in year 2023, in an update assessment made by a community effort called the Glamby team, we showed that for year 2023, the mass loss of glacier reached as much as 550 gigaton per year, so double the amount during the previous 20 years. And in this assessment, we showed that glaciers in the Alps in the Pyrenees have lost 40% of their volume in less than a quarter of a century. So just to illustrate that glacier mass loss is going very fast. So glaciologists have developed a different method to weight the glacier to measure their mass balance. Of course, the first one coming to your mind is based on in situ measurement. This has been used for decades to measure the change of mass of about now 100 glaciers on Earth. But of course, these 100 glaciers, it's difficult to know to what extent they are representative of the 200,000 glaciers or more that you find on the Earth's surface. And most of the measurements are made on small glaciers, which are easy to access. So this raises the question of whether those measurements in the field are representative. So the community has developed over the last 20 years several techniques to measure glacier from space, measure their mass balance. I don't have time here to go into detail of each of these techniques, but I refer you to a review paper we wrote back in 2023 in Report on Progress in Physics that detail each of these methods, its strengths and weaknesses. Here I will focus only on the last method, which is sometimes referred to as the geodetic method or the DM differencing method. This is a method that we've been using in Toulouse to look at glacier change. It gives high spatial resolution, as I will explain, and allow measuring glacier over a long time period at the global scale. To illustrate the principle of this method, I show this animation showing the change of the mer de glace. This is a glacier tongue in the French Alps between 2003, 2012, and 2022. This is derived from images and digital elevation model from Pléiades in 2012 and 2022, and SPOT5 in 23. I think you can easily see that those topographic data and the associated images can allow measuring the change both of the retreat of the glacier front with this yellow arrow here, and also the thinning of the tongue of the glacier, which is really obvious during this 20-year time period. So this is the technique that we are going to use, produce digital elevation model, topography of the glacier, and make the difference between them to look at glacier elevation change with time. We can integrate the elevation change over the entire surface of the glacier and convert this to the mass balance of the glacier with an assumption of the density of the material which was lost or gained, whether it is ice or fern. So the question you could ask is, why did we need a special project? Why did we need the Pléiades Glacier Observatory and a special acquisition program? This is because we rely on data, high-resolution stereoscopic data, such as from Pléiades. So they have a high potential for glacier monitoring, but they come from commercial satellites. So in the case of Pléiades, they are operated by Airbus Defence and Space. So there is no systematic acquisition program. The satellite will acquire images only when a user is asking for the satellite to do so and when the user is actually paying for it. So the idea of the program, supported by the French Space Agency CNES and this data initiative called Dynamis in France to facilitate access to satellite high-resolution images. So the idea was to make sure some images of glacier were acquired at the end of the summer, so the right time of the year. This is the time of the year when you have less snow on the glacier and where you can really distinguish the glacier and measure them as best as possible. And of course, the goal of the project was not only to acquire the images, but also to deliver the images and the digital elevation model to the community. A few words about the Pléiades satellites. So they were developed by CNES, operated by Airbus Defence and Space, as I said before. There are 2 satellites launched in 2011 and 2012, and they will fly until 2028. So those are very high resolution data with a panchromatic channel of 0.5 meter resolution that I will focus on today, and the multispectral images have a coarser resolution. And one characteristic of Pléiades is that it has a very high agility along its orbit. And as you can see here, you can see the same scene from 2 different points of view by rolling along the orbit, which permit to generate a stereoscopic pair. So 2 images of the same part of the ground, but from different point of view. How do those images look like? This is some of the first images we got over a glacier back in 2012. And what you can see here on your screen is you can see some black dots, which are aligned along a straight white line. This is end of the morning in August 2012 over the Mont Blanc area. And because we have a stereoscopic pair, so 2 images acquire 30 seconds apart, we can make an animation. And as you can see, some dots are moving, other not, towards the summit of Mont Blanc. And as you already guessed, these are mountaineers who are heading towards the summit of Mont Blanc. It shows the level of resolution that we get from those images. Maybe very interesting also for you is to note on the upper right corner, if I animate the images, you can see that the crevasses don't look the same in both images. This is the result, the stereoscopic effect, the fact that the images are taken from 2 different points of view. And this is the properties that we're going to use to generate accurate digital elevation model of the glacier surface. So this is the kind of data that we collect in the Pléiades Glacier Observatory program. This started back in 2016. And during the first 5 years, what we did is a first coverage of 140 sites that we selected all around the Earth. They are covered with a bit more than 280 stereopair. And in total, we cover 20,000 square kilometers of glacier, once again, outside the ice sheet. This is quite a lot. It's still small compared to the total coverage of glacier on Earth, but this is what we could get given the funding available in this program. And then after 5 years, we enter into revisits. It means that every 5 years, we map again a site that was seen 5 years before to look at glacier change over this period. So the product we deliver, with the example of an ice cap in Arctic Canada, we generate digital surface model or elevation model at 2 resolution, 2 meters and 20 meters. They are produced using a photogrammetric software, open source called Amester Pipeline, with 2 different algorithms. Very important point for us is that all our product, all digital elevation model are referenced to the Copernicus 30-meter global DM freely available from the Copernicus. And this is important. It means that it creates some homogeneity in our database. It means that the DM are readily usable because they can be compared to other data sources, other topographic data. And we also generate ortho images at 0.5 meter resolution or 2 meter for the multispectral images. As I said before, 5 years later, we come back to the sites, acquire some images, cloud permitting, of course, and then we generate a new digital elevation model. We make correlation, alignment of the DM, and can make the difference between them to generate an added value product, which is a map of elevation change. Here for this ice cap in Canada. In yellow, you have the stable terrain around the ice cap, and you can see that the noise level is very small. And in red, you can clearly see the thinning of the ice cap. And this is also a product we also provide to the community. We did quite some work in estimating the uncertainty of those DM. And we were lucky to have some airborne LiDAR, which is really the best topographic data that you can really get. And we were lucky to have them almost the same day as the acquisition from Pleiades, so the Pleiades Glacier Observatory product. So in Canada, they were acquired just on the same day, and in Norway, just 1 day apart. It allows, it's very important to have a reference data, validation data on almost the same day or within a few hours, because glaciers are changing constantly due to accumulation or melt. So you really want your reference data to be acquired within a very short time span. So we can, based on those reference data, we can make the difference between the PGO, Pleiades Glacier Observatory, DM, and the reference data, and look at those map of elevation difference. It shows an uncertainty of a few tenths of centimeters from our topography derived from spaceborne data. And very interestingly, we show that the off-glacier terrain is a conservative proxy for the uncertainty. It's important for us because usually you don't have LiDAR data at the same time of your satellite data. So it means that we can use the stable terrain around the glacier as a proxy for uncertainty and propagate this to the glacier terrain. If you want to know more about this acquisition program and the data we provide to the community, I invite you to visit our website, the Pleiades Glacier Observatory website. We describe the product. We describe also in detail how to access the data. That access is maybe not as easy as we would like, but still the DM are all open source. But you need to register to sign in to get access to the data. And we also advertise a publication coming from the community and make a gallery of a different product. When we have new nice images or new nice results, we post them on the website. And so this is the main site to visit, and especially a tutorial to get access to the data. And then you will be linked to a database which is based in Strasbourg, where you will have access to the digital elevation model, the elevation difference map. If you want the very high resolution images associated to the DM, you will need to sign a license because they are considered as sensible product by your defense service. So you need to register to sign a license before accessing to this data. Further detail are available in a paper we published last year presenting the whole program with a bit more, of course, at what I could present today. In particular, we look at whether those 140 sites spread all around the world, to what extent they are representative of the 200,000 glaciers on Earth. And to conclude, I hope I convince you that VM from high-resolution stereoscopic images are a key tool to monitor glacier change. As I said before, Pleiad is going to fly until 2028. So we have to think right now about the continuity of our monitoring program, and this should be ensured by a new constellation launched by the French Space Agency called CO3D. You can see a view on the left panel. This is 2 pairs of satellites which are dedicated to the measurement of the topography on Earth. And the first aim is really to build a global topography of the Earth at very high resolution. But for some of our sites, from glacier sites, we will have some revisit, more frequent revisit to go on monitoring the evolution of glacier. So this is on the short term, but on the long term, we are also advocating for a space mission that we name 4D Earth to really monitor every month or every 2 months the evolving topography of the Earth. This is not only a mission dedicated to glacier, it's also looking at the ice sheet, of course, and also any change that can occur at the Earth's surface. It could be change in the height of the canopy, it could be change of the Earth's surface due to landslide, due to volcanoes, due to earthquake. And yes, do not hesitate to contact us if you have any question. And I want to acknowledge Anne Guyet is also working with me in Toulouse on the Pleiad Glacier Observatory program. Thank you for your attention.
Thanks a lot, Etienne, for the presentation. It was really interesting to see the presentation of this project. And yeah, we have a few questions for you. So we'll go to the question. So the first one, so you answered already during your conclusion, so saying the project end in 2028. So you said there will be a follow-up to this project. Do you know for how long the project will last, or do you just know it will start in 2028?
Yes, so there's this new constellation called CO3D that should basically have similar characteristic as Pleiades satellites. So we are hoping, it's not secure yet, that we'll be able to maintain the measurement on those 140 sites on Earth to ensure continuity. For some sites, we hope to have a more frequent revisit than 5 years. Of course, it would be super interesting to look at seasonal change of glacier. So we always want to do more, but this is not going to be possible for all those sites. But for dedicated sites, we hope to have so a follow-up program at even higher resolution. And CO3D is, I think, planned for 5 or 7 years. This is the initial lifetime of the satellite, but generally, if they work well, it can be extended further in time, hopefully.
Okay, thanks a lot. So a more general question, how can you be part of a similar project? Or can we, as users, I guess?
How people can be involved, of course, people can be involved by downloading the data, working with them. That's the first step. The set of targets of the Pleiad Glacier Observatory is already set. We cannot add a new targets now because we want to go on monitoring those sites and ensure the continuity of those sites. So we cannot add more for funding reasons. But people can also order their own images. At least colleagues from European Union can access Pleiad at relatively reduced cost. So they can contact me if they want to acquire images of the site of interest, and maybe I can help.
Okay, thanks a lot.
Yes, good question. Other glacier, yes. So first of all, people can check the catalog. It's available. Everybody can check the catalog of Pleiades. It's named GeoStore. They can check if their site was acquired by Pleiades. The good news is that within a few months, years, the entire archive of Pleiad is going to be accessible. It's named a program by the CNES, which is named the Pleiad World Heritage. It's not the case right now, but if there is an emergency to get access to those data, people can, again, especially from European Union, can access the images in the catalog, there is a small cost associated to that, but they can access to that. And for colleagues outside Europe, basically they need to have a collaborator in Europe that can do they can access the data. And if they collaborate, it's possible.
Okay, thanks.
Alors, yes, Pleiades. It's a common problem from optical images that it doesn't work well in area of low contrast. This was the case in all images. There were 8-bit images. They were coded. They were problematic to process when there was little contrast. But to be short, with the new generation of satellite like Pleiades, you still have a lot of contrast, a lot of feature in the images in the upper accumulation area. So we have almost complete DM, even over the very flat ice sheet, even the very flat accumulation area. The DM are generally almost complete. And again, I refer to the review paper we wrote in 2023 when we detail that. So yes, and the errors are small, yes, in this upper part.
Okay, thanks. And so, yeah, the last question. So it's a more general question, so I think I can answer that. You showed that we can retrieve the data through your own website, Get Data, but will it also be made available through WEkEO? So on WEkEO, you will find Copernicus data mainly. Sometimes a few external data are also available on the website. So I don't know if this exact data will be made available, but in the meantime, you can use Etienne website if you want to check the data. So yeah, you will be able to, I guess it's explained on the website how to download the data. So yeah, if you want to have a look, you will need to go through Etienne website. And yes, so that was it for the question concerning your presentation. Thanks again for joining us today. And